AES is very regular, very regular. So what you see here is going to be very, very similar without taking any mention of the key. So some of you are here with me. Where is everybody, by the way? Is there like an exam or something? I'm missing you. Yes, Oren, I'm going to see a repetition of the operations on the graph. Great. By Kerchhoff's principle, I know that it's an AES encryption. So I see these operations repeated, but it doesn't help me anything right now. Okay, so let's try to develop this a little bit. AES, the instructions, if they are, the instructions don't tell me anything about the secret. But what does tell me something about the secret? Not the instructions. What's the other kind of thing you're processing? Two caches, instruction, and data. Thank you very much. So the data is telling me something about the secret. So we also know that the power consumption depends on the data, not only on the instructions. So this is like the roadmap. We're going to look at the data, and we're going to try to get the key out of the data. Because even though the instructions are the same, the data being processed using these instructions is secret dependent. So we can kind of try to look at this data and recover the key. So this is generally, this is my very optimistic plan. Of course, it won't work, but this is my plan. So my plan is I'm doing simple power analysis. So I have a device under test. I connect this device to my, I cut the power supply, I put a probe, or I put like an EM probe on top, and I have it encrypt a plaintext. I send the plaintext, and this device under test is going to encrypt it using AES with an unknown key. And while this encryption is happening, I am running my measurement device, my scope, and measuring a power trace. So this is a power trace. This is actually, this is a literal power trace of AES encryption, which the EICA, the University of Graz released online as part of the DPA book. So this is actually an AES encryption. So here is my output. This is the input to my algorithm. And now the next thing I want to do is recover the state bytes from the trace. Okay, so if we look at the evolution of the state begins with the plaintext and it ends with the ciphertext as it is evolving here. Okay, so I am going to, first of all, I assume that the state bytes are going to be moving along this. You remember we talked about this big bus, this big memory bus, which connects the CPU and the RAM. And I told you that this bus is really great for the side channel analyst because you can measure the data going across this bus. So I am going to look at the state bytes. So I see plaintext coming in and all sorts of data going across. And in the end, I'm going to see the ciphertext. And I'm going to recover the state bytes from the trace. So I'm going to have an array of size 16 bytes times 40. 40 is the 40 evolutions of the trace of the state. It begins with plaintext and it ends with ciphertext. I'm going to have an array of 16 by 40. And then I am going to recover, look at this evolution in state and recover the state. So this is my plan. So let's begin with the positive things about the plan, and then we'll see why it's very, very problematic. So first of all, can anybody tell me how do I, okay, why is it 16 times 40? So in AES, the encryption operation works this way. You have a 16-byte state array. You put the plaintext inside this state array, and you evolve this state using these this series of fundamental operations, which is add key, sub bytes, shift rows, mix columns, and add round key. You do this over and over again, modifying the state, mixing it really well with the key, mixing, and in the end, this 16-byte state array contains, voila, it contains the ciphertext. So I'm going to do it iteratively. So let's assume I have this fantastic attack setup which extracts the state bytes. So I have an array of 16 times 40. The first row is the plain text, and the last row, what is the last row? What is the last row? The ciphertext. Thank you very much. And in the middle, it's the evolution. Right. Thank you. Thank you. Why is it 40? Just count these fellows, okay? Just count. I had to implement this several times. You do 40 fundamental operations. Each round has 4 operations, and you have 10 rounds. And the last round doesn't have mixed columns because reasons. And there's an extra key mixing in the beginning. No, I begin with the plain text. Just count them, okay? I begin with the plain text and I end with the ciphertext. I have 40 evolutions. So, a little warm-up exercise. If I have this array, 16 times 40, how do I get the key? Let's do this shared whiteboard style. Which of these sub-rounds do you think is the best one to look at as an attacker to find out the key? So I don't think you should be referring to the powered trace itself, but here I have 40 operations. So which one of them should I be hitting as an attacker? So I have several people who are saying that sub-bytes is a great way of getting the key. So I want to attack sub-bytes. As an attacker, I have this array of evolving state. So I have the state before sub-bytes and after sub-bytes. And I actually know how to run sub-bytes. You just go to a lookup table and you look at the value of the S box and you plug in. So from the beginning, if I take the state before sub-bytes and after sub-bytes, doesn't really teach me much. But there I have Alex. Is that Alex? Hi, Alex. Is that Alex? Guest user who said the first one? It's not Alex? Who said that? Ah, it's Dimitri. Okay, fine. So Dimitri is saying that the first one, add key, is a very nice one to choose. Yeah, so this is, I'm not talking how you do it, but for some reason I was able to recover from this power trace all the state of AES. How I did it using some kind of signal processing trick that doesn't exist. Hint, hint. But let's assume I did it. So as Dimitri is suggesting, the first one. So the first one is add round key. And this is what I would do as an attacker because it's the most simple one to work on. So what is the beginning? What is the first value fed into the state register? That is the plain text. I know the plain text. And then this operation, you just XOR the bytes of the plain text with the bytes of the key, because this is how you begin with AES. You have to mix in the key, so you put the key in the beginning. So if I have the output of add key, and I have the plain text, how do I get the key out of that? Exactly, thank you, Sagi. I just XOR. So if I have plain text XOR key, and I have plain text, I XOR together, voila. So I have recovered the key from the state bytes. This is very nice. So if I have found a way to recover the state bytes from the trace, I can more or less get from the first round. I can get the key. Yeah. Okay. Anybody want me to repeat this? Should I repeat this? Yeah. I'll repeat it. I'll be happy to repeat it. So the first operation of AES is add key. You take all of the bytes of the plaintext, which are known to everybody, and you take all of the bytes of the key, which are the secret. Hold on with the round keys. I'll answer that tomorrow. This is the master key. It's not a round key. The first round, this case star, you see this case star means this is not add key. This is not add round key. This is add key or adding the big key. So if I am able, for some reason, to recover the 16 state bytes after add key, each one of these bytes is going to be plaintext 0 XOR key 0, plaintext 1 XOR key 1, until plaintext byte 15 XOR key byte 15. And now from these values, and from the plaintext, which I know because this is the model, I can XOR them together and get out the key. Now, I think I have 16 round keys, so that really depends on the key schedule of AES. I'm not really in AES 128. You have 10 round keys, but it's not really relevant. The first time you're going to meet a round key is here, but as Patrick Stewart says, it's too late because I've seen everything. You're already gone after you finish this first sub round. This add key. If you can get the state before and get the state after, yeah, K-star is the master. Yeah, that's also true because this is a very correct statement by Dimitri, I think. The key derivation function, which takes the round key, it takes the master key and gives out the round key, doesn't have any secret inputs other than the key. You can play it forward and you can also play it in reverse. So effectively, as soon as you recover one of the round keys of AES, it's equivalent to recovering the entire key. Thank you. That's an important statement. So I could just for the sport, I could also hit this add key or this add round key just as well. But this one is nice. It's handy. And you don't have a lot of memory in your scope. You have a trigger when encryption begins. You're gonna catch that. So this is like the very optimistic way of doing simple power analysis. Now, this isn't very practical in practice. And why is that? Does anybody want to tell me why is that, or should I just move on to the next slide? So before we talk about noise oil, hold on with the noise. Noise, of course, noise is this problem. Let's look at our assignment, our mission here. We have this trace. This trace is the output of the power consumption of the device under test. It has millions of points, right? It has millions of points. Somewhere here is this add round key, right? But we don't know how to get. We don't know when. So as you did here, we don't know that this kind of funny peak is actually sub-bytes. It could be something else. It could be that the encryption is only starting here somewhere. We don't know that yet. So we have a very difficult signal processing task of getting these leaks out of the trace. And even if we did get the leaks out of the trace, I want to show you a nice little piece of data, and again from the DPA book, a figure from the DPA book. So what you see here are this is was done on a very simple 8-bit microcontroller. This is the best you're going to get. So the x-axis here is time, and the y-axis is power consumption, equivalent to power consumption. It's voltage on the probe. And what you see here are repetitions of the same move instruction. So you're doing just move to memory. So this is an operation which has leakage, and if you look here on the right, this is a blow up of this. You see, this is a zoom in on this region. I'm going to zoom in a little bit also. You see that you don't have 256 different lines. If you're feeding in 1 byte, I would expect to have 256 different lines. How many different lines do I have here on this figure? How many lines appear here in this graph? You're supposed to type in a number now in the chat. 9. Thank you very much. Yeah, 9. So there are 9 different lines, 9 different power consumption patterns. So why do we have 9? Where did this number 9 come from? So there's a very easy hint here. This is the Hamming weight of the state byte. It's not the state byte. It's not the value of the state byte. I wish I could have the value of the state byte. But this is the Hamming weight of the state byte, which is, as we learned last week, and you also learned somewhere else, it's the amount of bits in the state byte which are equal to 1. So using my simplistic Hamming weight power model, which is about as good as a power model you can get in many, many cases, I don't learn the values of the state bytes. I learn the values of the Hamming weights of the state bytes. Is this clear? I'm not going to read out the bytes. I'm going to read out the Hamming weights. And just to make you feel a little more depressed, so this sounds, okay, you're saying, okay, well, first, before I had 256 values, and now I have 9 values, so, okay, I might have to repeat this a few times. Because, how much data am I losing? Just losing, half of the data, half of the accuracy, something like that. The problem here is that Hamming weights are very, very, very non-uniformly distributed. If you look at random bytes, you take a bunch of random bytes and you measure their Hamming weights, with very high probability, the Hamming weights are going to be either 3 or 4. You're not going to get 1 or 2. You're never going to get 0 or 8. It's going to be 3 or 4. Sometimes 2, sometimes 5. And why is that? It's a simple binomial reduction. You can try to find a binomial equation and run it. We don't have time to do it. But so why does the Hamming weight affect the voltage? Thank you for the question. I am going to need to restart my battery. Excuse me for a second. Some kind of laptop craziness here. A second. Okay. Very, very strange problem I don't want to debug right now. I need to restart my battery. Okay, looks good. Looks good. Okay, let's go. So, Sagit's asking, why does the Hamming weight affect the power consumption? And the reason is that, as I showed you last week, the bus between the CPU and the memory has multiple users, multiple components are allowed to write to this bus. So you can either have the CPU writing to this bus, that is when I'm writing to the RAM, or you can have the RAM itself writing to this bus. This is when the CPU is reading. So the CPU pushes to the address bus, what is the value of address 123, and then the RAM writes to this bus. And because there are two components sharing this bus, there is a convention that when you are not using the bus, you raise your outputs, you pull them up. So when nobody's using the bus, it's at all ones. And when somebody's using the bus, this component is going to be pulling down the bits that it needs to be pulled, the bits that need to pull down. And if you look here, you can actually see this if you are very, if you have very good sight, you can see that which Hamming weight causes the most dramatic changes in amplitude. Can you see? Can you look at this graph and tell me? You're now also expected to type in a value in your chat, a number. So it's a little hard to see, but yeah. So Oria is also, Oria already saw. The most dramatic changes are caused by Hamming weight 0, because indeed, to write a 0, you need to take all of the 8 lines of the bus and lower them down to 0. And when you're finished, you have to bring them back up to 1. So this is the very dramatic thing. And the Hamming weight of 8 is the most, it's the most gentle. There is some action going, but it's less. Yeah. So did I explain why the Hamming weight affects the voltage? Sagi, was that a good answer? Okay. So I have to redefine my my plan here, and my updated plan. So this is plan B. Is to capture a single power trace, awesome, and then to recover the Hamming weight of each one of the state bytes, because I can't expect to do anything else using my simplistic power model. And then I'm going to have a vector of 100 of 16 by 40, but each one of the values here is not going to be the value of the byte. It's going to be the Hamming weight of the state bytes. And then I need to recover the key from these Hamming weights. And this is actually something. This is how you do simple power analysis for AES. And